Alright, hello everyone. Welcome to the sixth and final boot camp of our part one of the DS3's boot camp for ML. And over the past few weeks, we've started from the very basics, intro to pandas, and we went all the way up to the intro to deep learning last week, where we started looking into a bit of basics of neural networks. That was taught by our one of our director of academics, Gursamar. So in particular, he mainly focused on the feed-forward networks. We didn't really get too much into the into any back propagation or anything like that. So in this week, we'll take another look into another kind of feed-forward network. In this case, it's called the CNN. We'll learn a bit more about it later. And then we'll also learn about how we use CNNs in the real world. In particular, we'll be looking into how it applies to computer vision. So this is kind of a brief rundown of what we're going to go through today, but in no particular means will it be fully static like this, as I'll be explaining a little more in depth than what the slides contain. So yeah, let's just start with like generalized computer vision. So does anyone here know what computer vision is or has heard of it? Yeah.
I mean, sort of like fundamentally, it's using a computer to, I guess, my understanding is that, process images, detect objects, maybe, or not classified, but, detect objects and deadlines and such.
Yeah, that's completely correct. Maybe.
Is Google Lens a good example of computer vision? Maybe.
Yeah, that's a clear example. We'll go into more like examples later on, but yeah, that's a great answer for example. Essentially, what computer vision is it's just basically a field of AI, where you're just making sure that your computer and all these systems are able to like interpret, analyze, and understand all this visual data that comes around the world. Whether it be images, videos, it doesn't even have to be those, it could be sounds or speeches. A lot of this is done within computer vision. And in this, very common and most of the time, like for sure used ML model would be a CNN. So what is a CNN? Well, first off, it's not the news network, American News Network, but instead it's called a convolutional neural network. An example of what a CNN could be like would be like number recognition. There's also another example of like speech recognition. Essentially, it's just a subset of deep learning, and it uses it's one of the main categories to do image recognition, image classification, object detection, and recognition phases. Very similar, like I mentioned at the beginning, to a basic neural network in the way that it's feed forward. But in this case, we'll have a few more layers, which we'll get into later, and it has some weights. So the three main layers that we'll be going through today will be the convolution layer, the pooling layer, and in this case for CNN, it will be called the max pooling layer, as well as the outer layer, which is most commonly referred to as the fully connected layer. So this is kind of like the main architecture of a CNN, which will obviously break down a lot. But obviously, before we get into three main layers of this architecture, we got to first think of our input. So based off what I kind of talked about at the beginning, does anyone have any idea of what particular inputs, what the input would be for this kind of network? Yeah. Images, yeah.
I was going to say images too.
Okay. Anything else?
I mean, specifically, probably like a 2D array with pixel value.
Okay. You mentioned 2D arrays. We'll get into that a little.
Maybe for each pixel value, like their color code.
Yep. So like we'll get a little more into that in terms of channels later. But yeah, images, it doesn't have to be exactly images. Like I mentioned earlier, you can have sounds too, right? Those can be translated into pixels as well, based off of frequency. So yeah, that's our input layer. Like this gentleman at the front mentioned earlier about like pixels, does anyone know how these pixels are represented inside of these with respect to these images?
Through arrays?
Yeah, they're arrays in a matrix, but like, what would these values be?
So for each pixel, we would have 3 values, and each of those values would be between and including 0 and 255.
Right, so it'd just be the RGB, right?
Yeah.
So the reason why he mentioned these 3 different pixels would be because of the RGB in an image, and these things are called channels, and we'll get into a little more of that, and how it's used in convolutional layers. Yeah, so convolutional layers. Essentially, convolution kind of comes from the term of the convolutional operator. Essentially, it's just basically saying take the dot product between 2 functions, and you get a third function. So an example of this, we can see of a convoluted layer of the result from an images. So we have our original image of this, I don't want to get this car wrong, but some Italian brand car. I can't tell if it's probably a Lamborghini, all right? If I got it wrong, then GG's. But anyways, and then so when we convolute it, you see it becomes much more blurry, but in this case, what our convolution is just doing is that we're trying to highlight like the main points, main focuses for this certain image. And so a little more deep dive into that part. In this, we typically use something called a kernel. Otherwise, sometimes you might hear of it as a filter. Essentially, it's kind of like a mini matrix. It's in which it has smaller dimensions than your original matrix, which is your image. And then essentially what this kernel or filter is doing is it'll be sliding across your image, and it has all these weights, as you can see from the image on the kernel. And essentially it's just taking all these values and sending it into a smaller convoluted image in which we can call the feature map. And like I mentioned earlier, essentially all it's doing is it's trying to make us highlight the most important edges or lines or anything that kind of pop up for from our original image. So I have a question. So do you think it's possible to have more than one kernel for each convolutional layer? Any ideas? Or do you guys understand what the kernel is doing? Or do you want me to explain a little more? Yeah. Okay, so let's think of it this way. So you have like Adobe Photoshop, or like you're on your phone, right? And say you want to blur something. So essentially what they're doing is they're taking a kernel specific a kind of matrix, and essentially they're scanning through and finding all the highlighted edges or something, and then like the process that they're doing is that they're taking all these highlighted focuses points, and they're just taking those, which will blur out all the details. That's kind of like an example. Like if you look at the image, like the yellow matrix, that's your kernel, right? That's your filter. What it's doing is it's just sliding across this general image, that input image, which is your image with your, I don't know, d by or n by m dimensions with pixel values, and it's just sliding over and like just taking the taking the highlight of you're just doing the dot product, right? Because that's what the convolutional operator means. And from those dot products, you get this new smaller matrices. And obviously, when we don't have as much defined points, that obviously becomes more blurred, which you can see in this image right here. Yeah.
So, for example, in this image here, if we assume the input image to be the red color code,
Yeah.
because it seems to be between 0 and 255,
Mm-hmm.
or each of those spots, but then we get the result to have values more than 255. Isn't that a problem?
Yeah, yes, okay, so.
I'm pretty sure you can scale it all at the end.
Oh, no, yeah. So like this is just the first layer of your convolution, and then after this you'll do max pooling, which downsizes everything. And then, so you run that again. You don't have a single convolutional layer, you have multiple. So everything like gets, like all your values, you'll eventually get downsized, as well as your dimensions will get downsized. Eventually you'll get to the fully connected layer, and that's when you can normalize everything. So back to is everyone kind of clear what a kernel does now? Okay, so back to my question, what do you think, it's possible to have more than one kernel in a convolution layer? Yeah?
Yeah.
Yes? Why do you think that?
Because what prevents you from applying the same operation multiple times, obviously.
Okay, yeah, that's fair. You can apply the same operations, but if you apply the same, what do you mean by same operations, actually?
Applying the same kernel matrix multiple times to the
Okay, yeah, you can do that, but you kind of end up with the same results if you have the exact same kernel matrices, right? But essentially, you got the right idea. We can have several kernels, right? Each kernel could be highlighting something different, right? We could be it could specifically look at horizontal edges in our image. Like, for example, if we look at this Lamborghini, if we're looking at the windshield, right? That could be a specific, we're looking at those edges, or no, actually that's not a good example. If we look at the road, all these edges, right? They're like vertical edges. That could be a single kernel. If we look at the bottom of the windows, those are horizontal edges, right? These are all different kernels that can produce different feature maps. Feature maps is essentially the result of applying the convolution there. Yeah.
How do we know which kernel is doing what kind of feature map?
So your kernel will be predefined, right? To do its specific operator on the original image. What do you mean exactly?
Like if you want to make up a feature map, we need a different kernel, right? And let's say this is not available in the literature. And we have to come up with a kernel matrix. How would we even know that such a matrix is able to produce that, map?
Are you asking how we construct the kernel?
Yeah.
We don't construct the kernel. The kernel is like a matrix of a bunch of parameters in which we can use backpropagation to train. And that's using gradient descent, or a form of it.
Right, because a lot of these times these kernels, they're already essentially it's just an operator, right? You're just using it to map for these feature maps. And then these maps, oh, I think I see what you're saying. Any of these node, the feature maps like a node in your layer. And you're asking about how to recognize different ones?
Yeah, kind of. For example, that previous kernel we had.
Yeah.
We know that this kind of smoothens the image, right?
Mm-hmm.
But if we had just ones in the first row and zeros on the second and third rows, how would we know what that does to the image?
We don't know what
we don't know, but when you apply the dot product, then you know, right?
We can't actually say for sure, because when we're training the neural network, we actually don't know what's going on. We don't know what's doing with the parameters. Okay.
Yeah. Okay. does anyone have any questions on this, still how the kernel operates with the original input image? Okay. Yeah, so also when we run this kernel and we convolve all these pixels, each pixel will have a nonlinearity function applied to it to make it more adaptable to like more complex to our data to find like for more complex patterns. In terms of nonlinear functions, we briefly mentioned this, or we didn't briefly, we actually quite strongly touched on this last week. Does anyone remember any nonlinearity functions? We went over it last week with Gersmark over there. You might have heard it in the activation functions part of last week. Okay, so like some of them like would be the sigmoid function. Another one would be like tan h. And then the most common one that we usually apply here is the ReLU function. Obviously there's a bunch of variants of ReLU, but we won't really cover that. But we'll get more into how ReLU is actually applied over the whole thing in a later part. All right, so now we'll get into a little bit more about the concept of so-called stride and padding. So essentially the weight of our matrix, which is our kernel here, moves one pixel at a time. And essentially we'll call this like stride 1. We see it in this animation down here. You know, it's just sliding across one by one, row by row. So like a question I have is, what if we increase the stride value? What do you think would happen? Anyone have any kind of like idea? Okay, so basically if we like increase the stride value, that means we're starting to miss some more information because we're like making our feature map smaller in that case. So essentially we're decreasing like the size of our final feature map image because we're like not doing it like a single stride at a time. So we're missing some boxes. So a solution to that would be padding. And essentially what we're doing is we're trying to add more than one layer of zeros around the image. And we can see that here. So when the input is now padded with zeros, then we'll get something called same padding, in which the middle 4x4, which is our original matrix, will still remain the same. All right, and that kind of covers the convolution layer. If we go back to our architecture, that was kind of the first part. And then now we're getting into the max pooling part. So this is another layer in our network. Like I said, it just comes after the convolution layer, like right after. And essentially the pooling layer is used to downsample, or in other words, like keep the most important parts and ignoring whatever's not important of our feature map that we produce from the convolution layer. And essentially what this is kind of doing is it's helping us like tackle with some overfitting. So when we do this, and what happens is we take another kernel, so another filter, and basically run it across our feature map that we produce from our convolution layer. And yeah, so it's kind of like here. We have a convoluted image, and we're taking another kernel, and we're running across that one, so we're smoothing it even more now. And then in terms of our cases right now with the CNN, what we want to do is we want to do max pooling. And what exactly is max pooling? So essentially max pooling is you just take the largest pixel value in the kernel region in each slide, each time you're doing your slide or stride, like I went through in the past slide, and you save it to another new feature map. Like I mentioned earlier, this is just trying to downsize the dimensions, or you can also call it like the spatial size of our previous feature map from our previous convolution layer. And again, we're just trying to highlight even more important parts of it, like to be more specific. Now, does anyone have any questions with the max pooling part? You guys kind of like get what we're trying to do with max pooling right after the convolution, right? Okay. So, do you guys, for the convolution layer and max pooling, like I said, they occur right back to back. But if we go back to like this, we can see that clearly that you don't have to have a single convolution layer and a single max pooling. You can have like multiple. How it works is you have your convolution, and then you'll have your max pooling. Then you have another convolution from that feature map, and then you can have another max pooling after that, even like your second convolution feature map. It doesn't really show it clear here because this isn't the greatest example, but essentially that's kind of what's happening over here. You just keep on taking these layers after each other. If you remember from last week, when we did our the basic neural network for the feed-forward kind, essentially there was the input and then there's the hidden layers. Essentially these are like kind of in those places of the hidden layers where you're just taking the convolution layer and you're just trying to find the most important parts through this process. Does anyone have any questions about these two layers? Yeah.
Or would you say it's more efficient applying max pooling after each convolution, or like doing max pooling after all cumulative convolutions?
I think after each time, because in that way you're downsizing every time. Like you're decreasing the spatial size, right? So it'll become you don't really want to do it after everything.
I'm pretty sure you end up losing more information if you do it before.
Oh, yeah.
Because the convolution layer is basically what you get your information with.
All right. So let's see what Arian had. All right. Well, before I get to the next part, I'll just continue a little bit from this part. So after we take all these different layers, right? This essentially leads us to something called abstraction, and based off of this new term called abstraction. Does anyone have a guess of what this term could mean? Think of literally what abstraction means. Think of how the word term abstraction means, and also how it plays into how we have more and more of these layers built up on each other in the network. Yeah.
I guess it makes the data easier to work with, but it just loses all meaning. If you look at that abstracted image, I guess, then you won't be able to understand much from it.
Yeah. So we're trying to focus more and more inside smaller details.
Yeah.
Yeah. That's kind of exactly what abstraction is kind of going for. Essentially, it's you're just extracting increasingly complex features from your input. So again, like you mentioned, even closer, smaller details, as you're moving through the network, right? Because at the beginning, our input image might be massive in terms of amount of pixels, but as we keep on getting smaller and smaller through all these layers, and we keep on downsizing, it gets to a specific, very small matrices that has a very specific feature from our entire input image. Yeah, so like as our layers, the number of our layers increase, obviously there will be more complex features detected, and that's essentially what the abstraction term means. All right, before we get to the output layer, there is one more layer. If we take a look back over here, it's the fully connected layers, right? I'll just keep it on the screen. So essentially here, what we're doing is we're trying to flatten all of our, just like we're trying to flatten our feature maps here. And then this will, this will serve as our input before we do our actual fully connected part. So in this part here, like before we actually do everything in the fully connected, we want to flatten all of our feature maps. Do you guys know what since our feature maps are matrices, right? And not only like you mentioned, if it's an image, it's not 2D, it'd actually be 3D because you have all your 3 RGBs. But so does anyone have know what flattening a matrix means, or yeah?
Basically turn your, n-dimensional matrix into this very long column vector.
Yes, that's correct. You just turn it into a 1D vector, right? So, all right. I'm gonna give you a scenario, and you're gonna try and tell me what the answer is to this. So, like, say I have an image, and then after all this, I get a feature map of 7 by 7 after all these layers. What do you think would be, and then what do you think would be the dimensions of the feature map of this image after all these layers, in which the resulting feature map would be 7 by 7? So this is just hint, bro. Just think of channels, like I mentioned earlier. Like I mentioned, it has to be, it's a 3D matrix, right? So what would be the full dimensions of this matrix? What do you think? It should be pretty simple, since I already gave you 7 by 7 earlier. Just think of the channels.
I'm guessing, but it's 49 times 1.
We're not trying to flatten it yet. I'm just asking for the dimensions right now.
Oh. Well.
So since you have 3 colors, right? RGB, that's 3. So it would be 7 by 7 by 3 now, right? All right. So with that knowledge, how would you flatten that? What would the resulting vector dimensions be when you flatten that 7 by 7 by 3? Yeah.
Guessing again, but 2 for 7 times 1. 2 for 7 by 1, as in the number of elements stay the same.
Number 2 for 7?
It's 49 times 3.
1 for 7?
Oh yeah, 1 for 7.
Yeah, okay, yeah. It'd just be 1 by 1 for 7, right? So you're essentially just flattening this 3 by 3, or no, sorry, this 7 by 7 by 3 into a 1D vector. And then now, each neuron in our FC layer, so our fully connected layer, each neuron here is connected to every input value, which is our flattened vector, by a weight. So I'm pretty sure this is our input vector here in this architecture. And then every one of these should be our weights. Right, okay. And then after this, we have to now apply an activation function. And does anyone remember what activation, what we described activation functions as last week? Or was no one here from last week? I kind of mentioned it earlier, but essentially what it is just applying a nonlinearity function to it to handle more complex patterns. So like I mentioned earlier, an example of it would be ReLU, but more commonly used in this case right here would be something called softmax. Essentially, you're just converting raw scores into like class probabilities. I'm not going to show the math examples, but you can also apply regression depending on the circumstances. And essentially, what we are doing is we're trying to make a prediction in this output layer. There's also some, like, a bit more advanced would include backpropagation as well as optimization, but I don't think we're going to go over that because it's kind of out of the scope of our level here at the bootcamp for now. If you are interested in some of that stuff, you could definitely come reach one of us. You can reach one of our directors too. If you are interested after the, like during break time or whatever, or you can also like message us on the Discord server. Make sure to be active. And over the break before our part 2. But yeah, like I said, backpropagation and optimization is a little out of scope, so we won't go through like much of it. So an example you might see later with the output layer would be, say you're trying to predict a number based off of something written, right? It will return whatever number it predicts it to be. Say you like have the number 9 on a piece of paper, right? Apply it through your model. Should return 9 as the prediction if your model was fitted properly. Like Divi said earlier, Google Lens. What would your output be? Your output would be just a text from whatever you got. Does anyone have like many more questions about how this architecture works in CNNs? All right. Now we'll get a little bit more into the applicational part, or like how we see this in real life. So, quick thing here. How do we decide the number of convolution layers and number of filters in CNNs? Filters, or also known as kernels, right? So in deeper networks, always better. At the cost of more data and increased complexity of learning. And you should initially use fewer filters or kernels, and you should eventually gradually increase it and monitor the error rate to see how it is varying. So when you start off with your network, you don't want too many kernels, so you don't want them to be like way too specific and like you're losing too much information. But again, you can monitor that. And very small filter sizes will obviously capture very fine detail, which we know from earlier with our when we were discussing the kernel stuff. And now into types of CNNs. So some CNNs you could work with, or you'll see in the future, would be image classification, object detection, object tracking, semantic segmentation, and instance segmentation. Also, like, not listed here, but you can also do like speech recognition, stuff like that. And then, so in terms of the image classification, we can use traditional CNN models, or there's also a lot of different architectures, like pre-designed by a lot of developers. In this case, we have like Linnet, AlexNet, and etc. All right, and then applications of computer vision. So how would we mentioned a little bit briefly at the very beginning how we can apply computer vision, how CNN plays its part into this. Now that we learned exactly what CNNs are, how do we think this can apply to, like, how do you see any of this happening around you in your real life right now? Like, what are examples of you see this stuff around?
Text to speech.
Text to speech, yeah. Anything else?
Give ChatGPT homework questions.
What?
ChatGPT, you can
Yeah.
upload images to it and then solve stuff.
Yeah, that's good. I was thinking, okay, yeah.
Anything having to do with self-driving cars?
Yep, that's good.
MRI scans.
Yes, that is correct. What? Okay, yeah.
Medical imaging?
Medical imaging, MRI scans are part of that. I was thinking like, say you're like speeding on a highway, what happens? How can you get tracked?
Oh,
I will say that I'm pretty sure that one's not AI. We've been doing that for a long time before AI. I think they just use a radar gun.
Okay, but like in terms of like camera,
oh yeah, the traffic cameras.
yeah, or like actually speeding wouldn't. I don't know about speeding because you'd be
No,
going a little too
I
fast.
think it triggers, like there's a certain limit, and if you cross it, it triggers the camera, and the camera just takes a photo of it. It's like
Yeah.
position to take a photo of your license plate.
That would be correct. So yeah, you mentioned a lot of these, like healthcare, very big in this. Nowadays rising, a lot of automotive industries. You can find a lot of startups in the U.S. who work with computer vision to develop all sorts of automation for these self-driving cars. Agriculture, something also very big. You might not think it's that big, but personally from Saskatchewan, you know, it's pretty big there, especially when you're covering large areas of land, right? You're not gonna go personally inspect everything. You can use, nowadays, you can use a drone that has these models built inside of it to help you identify stuff. Yeah.
Google Earth and Google
Google
Street
Earth.
View.
What about it?
There are also examples of computer vision. I think they're very powerful examples. Of
Oh,
computer
yeah,
vision.
Yeah. So in conclusion, you know, we kind of went through essentially what the general architecture, what exactly happens in our CNN. I tried to keep as much as the specific mathematical part out of it because I'm not sure if everyone here would be able to fully like keep up with it. But if you are interested in mathematical, once again, I'm trying to promote our server. Please ask questions, and we'll have people. Sorry, I'm losing my voice. We'll have directors who will answer you. Sorry, I'm gonna grab. We will have like VPs like myself or the other VP, and we'll have directors who will be there to answer any questions. Like anything you learned throughout this bootcamp semester, if you have any questions, please feel free to post them. A lot of people are willing to probably have the same questions as you, so it's good to like ask around and get prepared before our second part, where you're doing a project showcase. We don't want to wait around until that time, and you're still confused on a few concepts. Because then you're just you're a little behind, and it might put a little more stress on you. Especially if you guys are first years, you still have a lot of stuff. It's your winter semester. That semester was my downfall semester, so like I don't want you guys to suffer, especially in the dark days, because they're much shorter. But that kind of leads us into our break right now. And then after that, we'll be heading into our coding section, where you guys will actually get to do more hands-on and actually build your own model. So yeah, we'll have like a 15-minute break. Unfortunately, a lot of people on the team decided not to show up today, so we will not have any refreshments. There are washrooms, so feel free to use washrooms if you have to. But yeah, we'll be back in about 15 minutes. It's not the end of the thing.
Good. Good. Fantastic.
Break, and now we're gonna start the coding session. So for our coding session, we're gonna code up a convoluted neural network that is able to predict whether a handwritten image is a 0, 1, 2, 3, up to 9. So basically, it's we're going to be using a popular data set known as the MNIST data set. So let's get to that. So call this. Actually, I'm going to let you guys pull up your Colab really quickly. So I'm going to give you guys a couple of seconds to do that. And once you do that, you want to name your collab. Let's just call it Machine Learning Bootcamp Week 6. Right. Give you guys like 20 seconds to pull up the collab. And I hope everybody has their collab open. Now, the libraries we're going to be importing are, we want to import TensorFlow, which is basically our building blocks for our convoluted neural network. We also want to import matplot library, as always, because we always want to print out our, or rather graph out our results. So matplot.pyplot, and we want to call it PLT. Next, we want to import Seaborn, in which we're going to use this for our confusion matrix. If you guys remember what that is from classification, I'm going to recap what it is really quickly. So basically, a confusion matrix plots out, it's like a plot of your actually whether you got a true, or actually I can't remember exactly, but I'm going to move on, but I hope you guys remember what a confusion matrix is. Anyways, we're going to import NumPy as NP for matrix operations, as always. We also want to import pandas for data framing, import math, import datetime because we want to track how fast our convoluted neural network is learning. And finally, import platform. Yep. You got a couple seconds to do that. Now, you guys don't want to forget to run this code block because if you run everything else, everything's going to malfunction. So make sure you do that. Oh, and sorry, before that, you need to also, there's something else you need to do before that. So make sure you put this, actually, let's cancel this run block. So before you run the block, you want to import basically we want to use version 2 of TensorFlow, so make sure you do that. And then run this code block. And then you can run this. It's going to take a while. All right. Now for the next code block, let's see. We want to basically get our MNIST dataset. And luckily for us, the TensorFlow library has the MNIST dataset already set for us. So from TensorFlow, access Keras, datasets, and MNIST. It's a pretty popular dataset. That's what they provide for us. And now what we want to do after that is do the test train split. Likewise, luckily for us, TensorFlow makes it really easy for us to do the test train split. So let's call this pair the training pair. And then we also have the X-test pair, the testing pair. And then you want to set this equal to your data set. Then you want to load your data. Such. Do not forget to run this code block. Not load data. And there's quite a bit of stuff that has been loaded. Right. Now, once we get our data, we obviously want to know the dimensions of our data. So let's actually print out each of these X train, Y train, X test, and Y test. So let's do that. Let's print all of them out. So let's call this, let's see what our X train is like. And we want to see the dimensions of it. We are only concerned about the dimensions of it. And then just do the same thing with the Y train. Shape. xtest.shape. And finally, your y-test, as well as the y-test, as well as the shape of y-test. All right. Do not forget this. You want to format it nicely. All right. Let's see. So as you can see here, this indicates that we have 60,000 images in our training set and 10,000 images in our test set. This represents the dimensions of the image. So each image is like a number, or a handwritten number from 0 to 9, and its shape is a square matrix, a 28 by 28 matrix. This is just a one-dimensional vector, which represents whether a number is from 0 or 9. So like the actual numerical answer to the problem we're trying to solve. All right. Now what we want to do next is the following, and I'll explain it in a bit. So image, we actually want to save the image's width, original width and height, because we're going to be doing a lot of transformations through all these convoluted neural networks. And that information we're going to lose on the way as we do it. So we want to store all of that. Set it equal to xtrain.shape. And then image channel. We want to set our image channel to 1. And essentially, a channel's like your RGB values. So if we have 3 channels, it would be like RGB. We're only concerned about one image channel because it's all going to be binary. It's going to be black or white. All right. So let's actually print all of this out to have a sanity check. So I'm going to do that really quickly. Print out the image width. I want to print out image height and print out the image channel. Just for a sanity check. See if everything good. Yeah, perfect. Everything's good. Now, we want to actually observe what each of these data entries are actually like. So we can do that easily with the pandas library, accessing pandas. Then we want to turn, let's say, the first number inside of our training set into a data frame. So we can do that with pandas, like I said. And let's see what it's like. It's not very informative, is it? All you see is just a bunch of zeros and these random numbers. What do they even mean? Well, the thing we're going to do next is going to be pretty helpful in order to actually visualize it. This is actually like a contour map. It's a binary contour map. So like 0 represents all white, whereas 255 represents like all black. All right. So let's make another code block in order to actually. Sorry, did everybody copy this down? Who didn't copy this down yet, or who's behind? Okay, so I'm gonna give it a couple of seconds for you guys to copy this. All good? Nice. Okay, now we can move on. To actually visualize this, let's see if I actually, okay, everything's ran. Fine. To actually visualize this, you can use matplot by accessing plt.imageShow. It's not actually called imageShow, it's just called imshow. And we want to visualize xtrain, the first data entry at xtrain. And then, actually, I'm going to print this out really quickly so you guys can see what it's like without the extra parameter. So this is what it looks like, all right? Not very helpful. So there's another parameter you can include. It's called the contour map, or rather the C map. And what you want to set this equal to is plt.cm, which is short form for contour map, then binary. So let's see what it's like now. Yep, this is what we get. This is our image. Hope you guys are able to copy this down. Perfect. Does anyone have any questions so far, or good? All right, perfect. Now, the next couple of lines of code, we're actually going to visualize more of the data set, and to do that, it's somewhat complicated, but I'll run you guys through. So we want to display, let's say we want to display 25 of our entries. And let's say we want to display it as like a 5 by 5 square. So what I'm trying to get at this is that we have 25 of these images from our data set, and we just want to print out 25 of them, but we don't want to print out on the line. We want to print it on like a 5 by 5 matrix. Easier to visualize, right? So we can set the number of cells equal to math. So actually, we could just set this to 5. All right, that's like the square dimensions. Plot, figure, and then fig size. So this is just how big, like how many pixels large is our image. Now, obviously, we want to do a for loop to run through all of these 25 images. All right. For I, in range, numbers to display. We want to create a subplot, okay? We want to create, so as you can see, all the code is already provided for us, but we want to create a subplot with dimensions, number of cells, which is 5. We'll create a 5 by 5 subplot, and I plus 1 as our parameter. Now, as you can see, we have ticks down here. We don't want to do that, so let's actually set the x ticks to empty. And as you may guess, we can do the same thing for the y ticks as well, because we don't want to see ticks, we just want to see the images. Also, we want the grid to be false. We don't want to see grid lines on our image. And now we can show the image in the following code. X train at the ith index. And once again, contour map. It's going to be a binary contour map. Give you guys a bit of time to copy. Sorry, give you guys a bit of time to copy that. Actually, there's a bit more code. Then let's call this, because we actually want to know what the image is. So let's do this. Y train. Remember, these are our actual labels. This is representing what the image actually is. So underneath it would say like 5, representing this image, corresponding to y in the Y train set. All right. And obviously we want to do guilty dot show. Give you guys a couple seconds to copy this down because it's a handful of code. So actually, I'm gonna run it after I give you guys like 30 seconds to copy it. Our new matrix looks like, or rather, I should say a tensor, because now we added an extra dimension to our matrix per se. Channel that shape. So let's see what it looks like. And the loss function is decreasing, which is a good thing. That's what we want. Now, this is going to take forever, and you have two choices in this situation. You can just sit back and look at it compile, or you can be productive machine learning engineers and just move forward with code. And what we're going to do next is that we want to essentially graph out, as our APOC is progressing, how is our loss function, like how is our loss behaving? Is it decreasing or increasing? That's something important you have to do, so let's actually do that. X label, APOC number. Oops, you do not want to make a new code block. Give me a sec. You also want the Y label. And your Y label is the losses. Plotting a plot number with respect to losses. PLT dot, now you plot it. Training history. Training history data respects to the loss. Label train set. Train history. Sorry, it's not training history, it's train history. You do the same thing, just to save time, we're going to copy and paste it like this. But then instead of the loss, we want the value loss, which is essentially our APOC. This is the one display list. So after this finishes compiling, we're going to print this. It's actually, let's move this code block down here. And now what we want to do, we want to plot out the APOC number with respects to, it's a very simple change, just with respects to the accuracy, how the accuracy is behaving as the APOC progresses. So just change this to accuracy and the value of the accuracy. Such. Okay. All right. Make sure you put this in the queue so it can compile after it's finished. And now, yeah, essentially we're done that. Now we want to see how our model performs, and to do that, we want to import this thing called capture. Capture, which gives us a train loss. Now we need to track our train loss and train accuracy. Do that with evaluate our X train normalized with respect to our Y train. So just put this in the queue. And then after that, we want to print it out. So let's try to print out our train loss just to see what it's like. And this is also going into the compiling queue. Such. All right. Now, let's print out the coding block. So this is actually for the test set accuracy, training set accuracy. Now we want to do the same thing, but with the training set. So essentially we're applying our model on both the training set and the test set to see how it performs. It's like our validation set. Validation loss. Accuracy is equal to the model.evaluate. And we want to evaluate a model on our test set, our normalized test set, with respect to the Y test, all right? So we also want to capture this. Capture this to file. Then we can just print this out, just copy and paste it, just to save time. Do the following. Yeah. And finally, actually, there's a bit more, but after we train our model, we do want to use our model in other different settings. So what we can do is that we can actually save our model into our file section right here. And to do that, say, let's name it digits recognition. CNN file. It's the type of file it is. And we do model.save. Model.save with the parameters. Call it model name. And then save it as file. Yep. So once our thing finishes training, which is it's almost done, and as you can see, the accuracy is pretty ridiculously good. It's a 99.22% accuracy prediction. That's pretty insane, if I say so myself. And then if you ever want to load the data, you can just do the following code. Model, keras, model.load, model. This is if you want to load the model. Now, we want to see if our model actually works. And to do that, we can do the following. So let's call this our predictions. One hot predictions. And with our loaded model, we can predict, let's say, on the X test, normalize. Okay. history object is not subscript. So let's give me a second to see what the problem is. Oh, I need to access the, so just go back and access the history. It's a property of this variable as such. And then it should show you this graph. And as you can see, the training set data is decreasing and the test set accuracy is also, sorry, the loss is also decreasing. All right. Do the same thing for the accuracy. And as we want it, the accuracy of the test set is increasing, and as well as the train set. So that's exactly what we want. And our final accuracy is this number, which is pretty good. All right. So just yeah, let's try to run all these blocks. It's going to take a while. Yep, you can see the accuracy right here. This is on a training set. This is on our test set. This is our accuracy on a test set. This is the loss. Load probably has to be plural. Yes, this has to be plural. No. All right, I'll just show you what a confusion matrix is, and then I'll explain it more in detail. Confusion matrix. Matrix. Y-test. Predictions with your predictions. Because we're comparing our actual outputs with our predicted outputs. So that's essentially what the confusion matrix does. It compares the actual outputs, the actual data. So yeah, the actual outputs with our predicted outputs. Right. Let's store these variables into subplots. The figure size of it is going to be 9 by 7. Figure size. Then we're going to access the Seaborn library. It's going to call it was called the heat map. This is what we're going to use to plot our confusion matrix. Annotated, we want it to be annotated. The line width, let's call it 5. Let's give it number 5. Don't forget the comma here. FMT equals D. Square, we do want this to be a square, and the axis is going to be equal to x. Yep. So let's see what this confusion matrix looks like. So this is exactly what we want. If you remember from the classification session, we want it to be all on the diagonal. This is our correct predictions. So if you forgot by now, this essentially means the actual output is 1, but you predicted 0, and so forth. So all these off diagonals are incorrect predictions. This is like a contour which helps you visualize this better, like how dense these pixels are compared to the others. All right. And yeah, that's about it. That's about it. Yes?
Can you scroll a bit up?
Oh, do you need more time to copy this?
The one above. Yeah.
Yes. Actually, I think we have a bit more time. We have like 2 minutes. So you can just do CMAP equals to convert this into a binary image. Yep. Oh, sorry. Here it is. I'll let you guys copy this code, because this is the last piece of code covering. Give you guys until 6 to cover it, because that's going to be the end of our session. I'm assuming everyone has this copy down. And yeah, that's about it. Thank you guys so much for coming to this machine learning bootcamp throughout this entire semester. I had a lot of fun creating these slides as well as the exercises for you guys. And we're actually gonna host this bootcamp once again next fall. So if some of you guys are not actually in this bootcamp and you guys want to join this bootcamp, so just wait until next fall and make sure you guys stay in check with our DS3 Discord as well as our Instagram, because we're going to be posting a bunch of stuff there. Such as, one of the big ones is going to be like a part 2 to this bootcamp in which you're going to make different projects. And these projects are very integral to your career because you can put them on your resume. And yeah, that's about it. Thank you guys so much. I hope you guys, thank you. And I wish you guys the best of luck with all of your exams and whatever comes after this week. All right. Don't forget to fill out the form.
If you guys can just please fill out the feedback form for yours, then I'll put the attendance form after.
All right. That's about it? Yes. Nice. Yes?
Also, can you show the participation QR code again?
What's the feedback? Oh, the
Oh
participation.
no, this is the feedback form. I'll show the.
I think it's in the next slide.
Yes.
All right. I mean, I don't think there's really any point to this participation anymore because the camp's done. Wait, I don't know what. The reason why he's doing this is because he wants to Oh yeah, I gotta mention about the data fund. Also, on top of the projects that we're going to be creating in the part 2 of this bootcamp, there's also the datathon that's happening outside of this bootcamp. So just make sure you stay in touch with the Instagram, the Discord. We'll be posting a lot about the datathon. All right. Are we done with the QR codes? Yeah, and here's the feedback form.